In the first example for this learning target, we're asked to find all 6 trigonometric ratios for the following triangle. In this case, I guess it's triangles because we got part A here and then part B. So we'll knock out part A here and then we'll go for part B. If you're going to find all 6 trigonometric ratios, you're going to need to know all 3 sides of this triangle. We know it's a right triangle, so we're allowed to set up all these different ratios, the basic trig ratios, all 6 of them. We need to know the hypotenuse. Some of you know that this is a Pythagorean triple right off the bat, and so the hypotenuse here will be 13. Notice that 13 is larger than both 5 and 12. That's a great double check for you. You can make some mistakes here and there of thinking there's a Pythagorean triple when there actually is not. So if this side was 12 or the hypotenuse was 12, this wouldn't be 13. That just wouldn't make sense in the context of the problem. If you're having trouble remembering some of these Pythagorean triples, then you can also just use the Pythagorean theorem. So you could also say that 5 squared plus 12 squared is equal to the other side squared. We'll call it c. That's the normal variable to use for the hypotenuse. We've got 25 plus 144 is equal to c squared. 169 then would be c squared. We'll square root. We don't need to worry about the negative value here because we're talking about a length. And so you'll see that c will be the square root of 169, which actually will be 13. So you don't need to remember all of those Pythagorean triples. They can help your cause, though, by being very, very fast, and you'll alleviate any chance of making a mistake in here. If you do the Pythagorean theorem and you know the triples, that's an even better check that you're on the right track. And a Pythagorean triple, I guess I should just say, if you don't know, that's a right triangle where all of the side lengths work out to be positive integers, or you could say whole numbers. So sometimes there's some square roots in there. Anything that has a square root or a decimal, that would not be a Pythagorean triple. Now let's set up all of our trig ratios. So we'll start with the sine. The sine of theta is opposite over hypotenuse. Be very careful which angle you're talking about. It totally matters. So the sine of theta will be opposite over hypotenuse, so that's 5 over 13. There's no need to provide a decimal answer here. I like to do the reciprocal trig functions right away. We know that to find the reciprocal function of sine, the memory aid is to just change the first letter here, or the first letter is at least different. So it'll be the cosecant. And then the cosecant, you just take this and then use a reciprocal of the sine, so that'll be 13 over 5. The cosine of theta is going to be adjacent, which is 12 over 13. Again, easy to do the secant here. Remember that the reciprocal functions will have different first letters, so we just take our cosine ratio and use the reciprocal there, flip it if you will. 13 over 12 will be the correct value. We need to do the tangent next. The tangent is opposite over adjacent, so here's our angle. We need to go opposite, which is 5, over adjacent, which is 12. We also can say that the cotangent of theta then is 12 over 5. The cotangent and the tangent have a reciprocal relationship. Let's work on B here together. And this one may or may not be a Pythagorean triple. So part B, we have a right triangle. We need to verify that that's the case to set up these trigonometric ratios. Here's our angle. We've got, looks like the adjacent side. Here's the hypotenuse. And now we need to figure out what the other leg of the triangle is here. It doesn't matter what variable you use. I'm just going to use y. You could use b if you want, or a. That's another value or another variable you'll normally see there. So if we set up our Pythagorean theorem, and I don't think this is a triple, it's not ringing a bell, and so if it doesn't ring a bell, just use the Pythagorean theorem. We've got 7 squared, one leg squared, plus the other leg squared is equal to the hypotenuse squared. So we've got 49 here, plus y squared is equal to 81. We need to solve for y, so let's isolate this term. We'll need to subtract 49. So y squared will be, oh boy, let's see, 32 I think. And we'll take the square root. We'll work that up here so that you can see that on the video. And that's going to be just the positive value of the square root of 32. Great idea to simplify this. That'll help us later in simplifying some of our fractions. So I'm noticing that 32 can be divided by 16, which is a perfect square. So we could rewrite the square root of 32 as the square root of 16 times 2. After all, 16 times 2 is 32. When you have multiplication, you are allowed to split up this radical into two different radicals. And we now have the square root of 16, which is 4, and then the root 2, which needs to stay root 2. If at all possible, please use the exact value. This will matter quite a bit when you're doing calculations with these different values. If you decide to round part of the way through your calculations, what's going to happen to the calculations further down the road is they're going to be thrown off more and more as you use those rounded values. When you round something, you're losing or gaining, depending on which way you go, some value that's not originally there. So be very careful with that. We're going to really try to get this exact value in our class. Now that we have all three sides of this right triangle, we can set up our ratios. We've got the sine of theta, which is opposite 4 root 2 over hypotenuse. Almost did the adjacent there, that'd be the tangent. So we've got opposite over hypotenuse. We can now also do the cosecant. That's 9 over 4 root 2. Sometimes you're going to be asked to clear this radical out of the bottom. It's a really good thing to know how to do. So we'll just multiply by root 2 over root 2. After all, we're multiplying this value just by 1, so we're not changing its worth. We're going to change the way it looks here, but not its value. So we've got 9 root 2 in the numerator now. And in the denominator, we're going to have 4 times 2. The square root of 2 times the square root of 2 is 2. So 4 times 2 is 8. If possible, we should simplify this part, but we don't have to because we can't. We'll do the cosine now. The cosine of this angle is adjacent over hypotenuse, so that's 7 over 9. And then it's nice and easy to do the secant at that time as well. That's 9 over 7. The tangent is going to be opposite, which is 4 root 2, over adjacent, which is 7. Can't simplify this the part that's outside of the radical. Now we can go to the cotangent. We can take our tangent and just use the reciprocal there, 7 over 4 root 2. We'll need to do the same thing we did here with the cosecant, clear out that radical in the denominator. So this is 7 root 2 over 4 times 2, or 8.